Hi, today we'll discuss Unit 5 concept code optimization in compiler design. See here, code produced by any compiling algorithms can also modify that can make the to run the faster or take less space or both. So to make code to run faster or to make the space improvement by doing some transformations, the improvement of the program transformations in traditionally we'll call it as optimization. Compilers that apply code improving transformations are called optimizing compilers. So here the optimization can be classified into two categories: machine dependent optimization and machine independent optimization. The optimization can be done any level of the compiler, any phase. It can be applicable in any phase of the compiler. When it is a machine independent optimization, program transformations improve the target code without taking the consideration of the properties of the target machine. When it is a machine dependent optimization, here the target machine properties are required based on register allocation, utilization of the special machine instruction sequences like that. These all comes under machine dependent optimizations. When you perform the code optimization, there is some criterion you need to follow. What is it criterion is here? When we transform the code, normal code to optimized code, whenever the transformations are applied, the semantic equivalence of the program should not be changed. We should preserve the semantic. If you are transforming by changing the meaning of the program, then it is useless. The algorithm should be modified, should not be modified here. If the algorithm is modified, it will perform some other task instead of doing the task. So algorithm should not be modified. Transformation on average. So while changing a small part of the transformation can't improve that part, but overall program execution speed up will improve. So that is one criteria. Next, so here transformations should be very good effect to the program. This criterion of the. So where and how will optimize? So I told you, optimization can be done in any phase of the compiler, at source code level or at intermediate code level or at target code level. When a source code means who will involve in the source code? User will involve. When it comes to when the source code is converted into intermediate code, it means that will done by whom? Compiler. So the intermediate code and the target code level, if you are doing the code optimization, the duty of optimization will be done by the compiler. So here at intermediate code level or at a target code level, if you are applying an optimization, here at a target level we'll go for the register allocation of, that is machine dependent optimization will be done at target code generation. When you are performing the optimization at intermediate code level, that depends upon the machine independent. So it will done by the compiler. So how the optimizing algorithm will organize means, first it will analyze the control flow, then it will goes for the data flow analysis. After these two analysis is completed, then it will go for the transformation. Control flow analysis, data flow analysis, and then transformation. So here what is control flow means, here we'll decide the structure of the program, where the control structure of the program, how the flow graph is going on from one level to another level. So here data flow means how the data is transformed from the one block to the another block. Is data is live or is data is dead? So that analysis is known as data flow analysis. When we go for control flow analysis, a flow graph is built based on that control structure. Transformations, what it will do means, it will help in improving the code without changing the actual meaning. That is known as transformation. So when we want to do the control flow analysis, the intermediate code level code, what it is converted is constructed as a flow graph. So a graphical representation of the 3 address code is called as the flow graph. The nodes in the flow graph. The nodes in the flow graph represents what means here a basic block. Actually, when you go for syntax tree and semantic tree, each node represent each variable. Whereas in flow graph, we'll draw the graphs based on the blocks. So each node in the flow graph represent a block. So to construct the flow graph, one basic thing is we need to identify the blocks first. According to that blocks, we'll construct the flow graph. So these flow graphs, where it will be useful means by using these flow graphs, you know how the control flow and data flow is done from one block to another block. How the analysis, the analysis, control flow analysis and the data flow analysis is easily be done when the flow graph is constructed. And based on that analysis, we may apply local level optimization or global level optimization according to the analysis of the data. Here, so main thing to construct a flow graph, first of all, from the intermediate code, we need to identify the blocks. After identifying the blocks, how the flow is going on, according to this, the flow graph is constructed. So here a basic block is nothing but a set of statements. So a basic block is a set of consecutive statements where how these statements will execute sequentially. It won't go to anywhere else. That set of statements consecutively executing sequentially, those set of statements will categorize into single block. Okay. In this block, every statement should execute one by one. Then we'll call it as that is a block. A sequence of statements which are executing sequentially one by one without going to here and it, then those set of statements we'll call it as block. So for example, we have one statement here. What is that? A equals to B plus C into D by E. So this is the source code. When you convert into an intermediate code, this is our intermediate code. So first we'll calculate C into D completed. After that we should divide by E this. C into D is stored in some temporary variable T1 by E. After that, it should be added to B. Then the result is again transformed into a variable A. So here there is nothing jump from one statement to another statement. All statements are executing sequentially one by one. Then I can say that this all 4 statements comes under a single block. So all these statements corresponded to a single basic block. So as it is a 3-4 statements, a very small expression, we can easily identify the block. If we have some lengthy intermediate code, then how to identify a blocks. So every statement, first statement in a block, we'll call it as a leader statement. So if the duty of identifying the leader statement completed, so one leader statement to another leader statement, we'll call it as block. See, procedure to identify the basic block. So here, first of all, in a given 3 address code, first we'll identify the leader statements. Then we group the statements from one leader statement to next leader statement. First statement in the program is always a leader statement. Next, any statement that is a target for conditional or unconditional statement, that statement also will call it as leader statement. Any statement immediately follows conditional or unconditional statement is called it as leader statement. So based on these 3 situations, from the 3 address code, we divide into blocks. So for example, here we have one source code. The resultant 3 address code is this one. Okay. Now, according to the first point, always first statement is a leader statement. So this is a leader statement. According to rule 2, statement 3 and statement 12. Why it is leader statement is, it is statement 3 is for initialization of the loop here. So that will start as leader, and as soon as loop completes, whatever statement we got, that is known as leader statement. So that is a leader statement 3 and 12. Next, according to rule 3, statement 4 and statement 12. Statement 4 and statement 12 is a leader statement. Rule 3, what is that? Next to the statement, to the loop, it is a leader statement. So here, for this 3 address code is written. Then for these 3 address code, identify the leader statements. After identifying the leader statements, it is taken as blocks. So this is a basic blocks. The flow between these blocks, if you draw like this, then it will call it as flow graph. Then it is called as flow graph. So here, using DAGs for each basic block is represented. So DAG is a useful data structure. It is a data structure to implementing the transformations within a basic block. So here, within the basic block, if any transformations are required, that can be easily done if you construct a DAG for each block. It is, when you have constructed a DAG, it is easily helpful to identify the common sub-expressions within a block. And a DAG has nodes. As a DAG is a graph will contain nodes. Then how the DAG nodes will be there? The leaf nodes of the DAG always be identifiers or constants. If operators are arithmetic, then it always require what value? R value. So without R value, arithmetic operators cannot be done. And some nodes sometimes referred as a sequence of identifiers from labels. The interior nodes represents the computed values. See here. For example, we have one statement A is equals to B operator C. Now we'll draw a tag for this statement. Check whether, if you want to draw a graph for any nodes, first of all, we'll check whether the nodes are existed in the graph. If already existed, that will be taken directly instead of taking a new node. So that is the first point. Check whether there is a node with same values as B and C. Then what we will do? We'll append the label A to that node. Next, if that such node does not exist, if the node is not exist, what we'll do? We'll check whether the existing nodes for B and C is having any leaf nodes or any internal nodes. Then create a new node. If it is not there, what we'll do? We'll create a new node for operator and add the left child and B child, right child as B and C respectively. Label. So label this node with A. This would become the value. Suppose first point is not satisfied. The second point is not satisfied. With the third one is not, that means already node is eligible. Then what we will do means, which was we previously marked, will make it as a number A0. The newly entered node will take it as A. So this is a construction of an DAG. How will construct mean? For each node, first of all, we list the identifiers and attach to it. So for example, if I am having I less than 10, go to L1. So it is about like this, case 1. If node B and node C are undefined, what we will do? We will create a leaves for B and C respectively, and we'll add a node B and node C these nodes. Suppose if we are having A equals to node B is undefined, it will create a leaf node. But node A is defined, no? We'll append these list of identifiers found in the node into A. So here just copy. We are copying A equals to B. So node B is existing node. Construct a DAG, delete it from the list and attach the identifiers for the node. See this example. After identifying the blocks, for each block we need to draw the DAG. So for I equal to 0, nothing. But n is equals to 10. Then n minus 10. N minus 1. N minus 1. N and 1 are leaves. Operator is a 10. That this operation represented by T1. Next, for this no need. Next, come to here. T2. T2 is what? I into I. So, same thing it is repeating like this. 3 is what? 4 into I. So, here already I is available. You can retrieve this one and you take one more ID 4. Will multiply it, that is stored in T3. Okay. Next, T4 is equals to T2. So, T4 and T2 are same. So, where is T4 here? T4 is T2. So, comma T4. See, T2, T4 like this. Next, T5 is equals to I plus 1. Again, I is already available before that I into I. If like this available, the previous one which is visited will make it as I naught. So, it is I naught. Next, I is equals to T5. T5 is what? I plus 1. First of all, I plus 1 should be done. I plus 1. Then, it is named as T5. Then that one we are equaling to I. After that, we'll go to step 3. So, these are the introduction for the concepts which are required in the optimization. Next, we'll see the principal sources of optimization. Principal sources of optimization. So, a transformation which is applied either in local level or global level, whatever transformation you applied, we'll call it as optimization. So here, when you are performing any type of transformation, it depends upon the optimization techniques. So first technique is function preserving transformations, structure preserving transformations, algebraic transformations. For under functions preserving transformations, we'll have the common sub-expression elimination, copy propagation, dead code elimination and constant propagation. Common sub-expression elimination means if any expressions are common in a source code and nothing is changed between these two expressions, then we'll call it as common sub-expression. If like that common sub-expressions are there, we should eliminate that one. Next, copy propagation. So, we'll see an example on common sub-expression. See here, C is equals to A plus B. F is equals to A plus B. Between this C and F, there is no change on C and F. Then we'll call it as common sub-expression. Next, here A into C, here A into C, here D into D, here D into D. So, for this A into C also, there is no common expression. For this D into D also, there is a common expression. Instead of taking all these twice, we'll calculate first time and we'll look for value to do. So, I calculated T1, A plus B, then A into C, then D into D as T1 and T2. Same thing is copied wherever A plus B is there and A into D is there. So here, when a statement, copy means what? We are copying from one statement to another statement. So as soon as if a copy statement is encountered, then techniques how it will apply later, the use of variable A within the use of B is original values and do not change after this assignment. The technique can be applied locally or globally. So here what they will do, D equal to C. So instead of C, instead of D, D is a C, wherever C comes, wherever D comes, we will apply C. So here, see, G plus A. Similarly, E and G. Wherever G occurs, we apply E. So, like this. Now when you are seeing this one, we thought that there is a common expression. So later on what they will do, they'll divide it based on the expressions and they constant means here if the, for example, see this program, pi value is 20/7. We know already every time the constant value pi. Then directly if you give the number itself to the ticket or anything, then it will take the normal, it will take the instead of substituting the pi value, we can take the direct value so that it will decrease the time of execution. See here, instead of 22/7, I can say that 3.14. Instead of taking like this, I'll take here 3.14 into RR. And next time here pi R. So instead of taking pi direct, 2 pi R. So instead of taking 2 into pi into R, if you calculate 2 into R, whatever value I am getting, that I can substitute. This is known as constant propagation. Now, when you see in a program, if you write, it may contains loops or it may contains other than loops. But if a program contains loops, that certain statements will repeat for some time, so it will take more time for the execution. Is there any possible to apply the optimization technique at this level, then we'll at loop level, then we can say that it is a loop optimization. See here, int I equals to 0, I less than 1000, I plus plus, x is equals to x plus y by z. So instead of this, if we take total number of statements, it will take 4000. If we are taking a frequency execution, it will take only 1000 times. So this makes less amount of time. So inefficient code generated in loops are various reasons. Why? Because induction variable usage, unnecessary computations made, and using high strength operators inside the loop. So what are the techniques we can apply in the loop means? Code motion or elimination of induction variable. See in this one, every time we are calculating y by z. So instead of calculating 1000 times y by z, before the loop, if we calculated and the same values kept it here as like that, then the execution time will be improved. Similarly, induction variable and strength reduction. So what is induction variable? So induction variable are those variables used in the loops. Their values are in lockstep and hence it may be possible to eliminate all except one. So that is known as induction variables. Every time the value of j, you see here, every time the value of j will decreases 1 and that of t4. So y, the yj value is decreasing means here every time it is multiplied by 4. If possible, try to represent statements. Suppose x is equals to x plus 10. Instead of that, you can take x is equals to x and x is equals to y. So if we want to represent a 3-address statement in a graph, then we'll use a flow graph. So flow graph is useful for constructing the code generation algorithms. How it is, you'll check it. So to construct the flow graph, first of all we should require what is denominators. So what is the definition of the denominators, that we'll see now. So denominators are used to identify the leaders in control flow. So according to the denominators, we can identify the leaders. According to the identifying the leaders, it will be divided into programs. So here, if a node D is dominating a node N, will directly represent as D dom N. See here, when we say dominator is, first of all, this is a graph. Now, when anything is passed from the node, and that is known as reader node. So here, through one only, all the elements should pass. So dominator of one is not, who is not there, because node itself is a dominator to all. Nobody will dominate the nodes. So similarly here, 1 is to pass 3, I should go from 1 to 3 or directly 1, 3. So here 2 and 3 is dominated by 1. So 1 dom 2 and 3. Next, to go to 5, either I should go 1, 2, 3, 4, 5 or 1, 2, 3, 4, 6. So I can call direct dominators as 5, 6, 7 is 4. Next, to come 9, I should go like this or like this. Then for 9, I will call it as 10, 1, 8 like that. And so here for 9 and 10 dominator is 8. For 9, 10, 7 dominator is 7. For 5, 6, 7 dominator. So here we can do the list. This is known as dominator T. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.